Welcome to this session on regression diagnostics and influence statistics in Stata, a practical guide to specification, fit, and robustness. This slide introduces the core concepts we will explore, focusing on ensuring our models are accurate and reliable. The visual highlights the impact of a single influential observation, the orange dot, on a regression line, illustrating how it can pull the fit away from the majority of the data. We will cover three key themes. First, detecting misspecification using the Ramsey reset test. Second, managing multicollinearity through the variance inflation factor, VIF. And third, identifying influential observations using metrics like Cook's D and DFBETAS. By the end of this guide, you will have a systematic approach to diagnostic checking in Stata.
Not all data points are created equal. In OLS regression, some observations hold much more power over our results than others. This slide visualizes why. Look at the left graph. Point A is far to the right in terms of X. This is high leverage. However, because it follows the general trend, the solid regression line remains close to the dashed counterfactual line. Now, look at the right graph. Point A is still a high leverage point, but it's also an outlier in Y. This combination results in high influence, where the regression line is visibly distorted. Technically, we define outliers by their residuals and leverage by the hat matrix. Influence is simply the product of the two. Failing to identify these points can lead us to draw entirely wrong conclusions from our analysis.
This slide outlines a systematic diagnostic flowchart for moving from an initial OLS regression to a final diagnosis of model health. The process begins with running the OLS regression using the regress command. From there, we follow three main stages of diagnostics. First, we check if the functional form is correct. This is our model specification check, typically performed with the Ramsey reset test via the SStat-OBO test command. Second, we verify that variables are independent by checking for multicollinearity, which affects model stability. We use the VIF command, SStat-VIF, for this. Third, we hunt for unusual observations. This involves two paths, checking location in the X space for high leverage using the hat matrix, and checking for outliers in the Y space using studentized residuals. Finally, we synthesize these findings to see if any observations significantly distort the model, evaluating both global influence through measures like Cook's D and parameter influence using DFBETAS.
This slide breaks down the taxonomy of anomalies to help us distinguish between leverage, outliers, and influence in regression diagnostics. First, on the left, we have leverage, which refers to extreme values in the predictor space, or extreme X. It is measured by the distance from the mean of X, using the hat matrix. Think of leverage as the potential of a data point to tip the model, much like the person sitting at the far end of the seesaw in the icon below. On the right, we have outliers, or extreme Y. These are observations with a large discrepancy from their predicted values, identified using studentized residuals. Visually, an outlier is simply someone standing apart from the crowd. The intersection in the center is influence. Influence represents the actual impact an observation has on the model's coefficients. It is the product of both leverage and residuals. We quantify this using metrics like Cook's D, dfits, and dfbETAS. To remember the difference, leverage is potential, while influence is the realized effect. An observation can have high leverage without being influential if it falls perfectly in line with the rest of the data. However, when a high leverage point is also an outlier, it significantly weighs down the model's results. This summary table acts as a quick reference guide for your Stata diagnostic toolkit. It covers everything from overall model health to the impact of individual observations. First, we use SStat-OV test for the Ramsey reset test to detect specification errors. A p-value under 0.05 is our warning sign. Next, SStat-VIF helps manage multicollinearity, with a VIF over 10 indicating severe issues.
Moving to observation-level diagnostics, the HAT matrix identifies high leverage points in the X space with a threshold of 2K over N. Studentized residuals, found using predict bar, re-student, flag outliers in the Y space when absolute values exceed 2. For overall influence, Cook's D uses a 4 over N threshold. To see how individual coefficients are affected, we use DFBETA with a threshold of 2 over the square root of N. Finally, CoV-radio assesses the precision of our standard errors. Together, these metrics ensure your regression results are both valid and robust. This slide focuses on two key diagnostics for ensuring a regression model's structural integrity: the Ramsey reset test and variance inflation factors, known as VIF. The Ramsey reset test is used to detect misspecification, such as omitted variables or nonlinear relationships. By testing if nonlinear combinations of fitted values add explanatory power, it tells us if the model's form is adequate. In the example provided, the p-value of 0.002 leads us to reject the null hypothesis, concluding that our model is misspecified and requires adjustment. Moving to the right, we address multicollinearity using VIF. This metric quantifies how much the variance of an estimated coefficient is increased because of collinearity with other predictors. As shown by the formula, when a predictor's correlation with others is high, the VIF increases dramatically. Our specific reading of 12 sits in the danger zone, indicating that multicollinearity is significantly destabilizing our coefficient estimates and must be addressed, perhaps by removing redundant variables. To identify outliers effectively, we examine two dimensions: leverage and residuals. Leverage, derived from the HAT matrix, measures an observation's distance from the center of the X data. High leverage points, bounded between 1 over N and 1, have the greatest potential to tip our model. Residuals, on the other hand, look at discrepancies in the Y direction. There is a clear hierarchy here. Raw residuals are simple but unit-dependent and difficult to compare across different models. Standardized residuals normalize these by standard deviation, but they can suffer from masking if an outlier pulls the regression line towards itself, making its own residual look smaller. This is why the studentized, or jackknife residual, is considered the gold standard. By calculating error variance without the observation in question, it prevents severe outliers from hiding behind an inflated error term. Remember the key insight. If the absolute value of a studentized residual is greater than 2, it's a red flag for an outlier that needs investigation. In this slide, we examine global influence, which quantifies how much the entire regression model changes when a single observation is removed. The standard metric for this is Cook's distance, or d sub I. Looking at the formula, we see it as essentially the product of two elements: the discrepancy, which relates to the size of the residual, and the leverage component. A point becomes highly influential primarily when it has both high leverage and a large residual, though an extreme value in either can also trigger a high d sub I. We also have other metrics for comparison. Cook's D, with its common cutoff of 4 divided by n, focuses on the aggregate change in coefficients. DFITS measures the scaled difference in fitted values, with a cutoff of 2 times the square root of k divided by n. Lastly, Welsh distance offers an alternative weighting, which is particularly useful as a robustness check to ensure no single metric is misidentifying influential points. Moving from global influence to specific parameters, we use DFBETAS and CoV ratio. DFBETAS, or difference in betas, allows us to drill down and see how much a specific coefficient, like education, changes when one observation is removed. As seen in the bar chart, if the education coefficient drops significantly after deleting observation I, that single data point might be driving the entire effect. A standard threshold for concern is an absolute dfbeta value greater than 2 divided by the square root of n. On the right, we look at CoV-ratio, which measures the impact on precision, specifically the standard errors. Think of this through the confidence ellipses shown. A tight blue ellipse, where CoV-ratio is greater than 1, means the observation improves precision. A wide, bloated orange ellipse, where the ratio is less than 1, indicates the observation is damaging precision by increasing standard errors. We typically flag observations falling outside the threshold of 1 plus or minus 3k over n. Now, let's see how we actually generate these statistics in Stata using the predict suite. The core syntax is straightforward. Predict, followed by the name you want to give your mu variable, and then the specific diagnostic option. As shown on the slide, options are categorized into influence, like Cooks did and hat, residuals, like our student, and precision, like Cove ratio. For those who prefer a point-and-click approach, the post-estimation dialog box shown on the right provides a user-friendly way to select these options without memorizing the syntax. Generating these variables is the first step before we can visualize them in diagnostic plots. Now that we've covered the theoretical underpinnings, let's look at the practical implementation in Stata. We'll focus on post-estimation commands and an essential data preparation checklist. For post-estimation, the SStat suite is your primary tool. SStat-ov test runs the Ramsey reset test to check for omitted variable bias or nonlinearity in your model's functional form. SStat-vif assesses multicollinearity by calculating variance inflation factors. Additionally, the dfbeta command is a powerful way to automatically generate influence variables for every regressor in your model. However, good diagnostics start with clean data. Our data preparation checklist includes: first, inspecting variable types using describe; second, checking for data entry errors or extreme bounds with summarize; third, identifying missing values with miss-table summarize. Keep in mind that list-wise deletion of these values can bias your results. And finally, performing necessary transformations, like logging variables to fix skewness before running your regression. We'll start our practice by loading the classic 1978 automobile dataset and running a baseline regression to see if weight, length, and foreign status explain car price. Our initial output shows an R-squared of 0.50, but the results raise some questions. Specifically, the coefficient for length is negative and statistically significant. Does it really make sense for a longer car to be cheaper? This puzzling result is why we need diagnostics. We need to find out if these coefficients are truly reliable or if the model foundation has flaws we haven't yet uncovered. In this second practice step, we examine the model's specification and collinearity using two key Stata commands. First, we run the Ramsey reset test with SStat-ov test. The resulting p-value of 0.0002 indicates a clear failure. Our model is significantly misspecified, which points toward omitted variables or nonlinearity that hasn't been accounted for. Next, we check for multicollinearity using SStat-vif. Notice the VIF values for both weight and length are 8.22. This high collinearity is a major warning. Because these two variables essentially measure the same dimension, the physical size of the car, having both in the model creates redundancy and can make our coefficient estimates unreliable. Moving to step 3 of our practice, we use the lvr2plot command in Stata to create this leverage versus squared residual plot. This visual diagnostic is invaluable for identifying specific problematic observations. Take the Cadillac Seville at the top left. It has a very high normalized squared residual, meaning its price is much higher than our model predicts, making it a clear outlier. However, its low leverage suggests it might not be pulling the regression line too far from the rest of the data. On the other hand, the Lincoln Versailles in the bottom right has high leverage due to its unusual weight and length, yet its price fits our model's prediction perfectly, as shown by its low residual. The most critical area is the top right danger zone. Any observation landing here would have both high leverage and a high residual, meaning it exerts a massive pull on the regression coefficients and can significantly distort your results. Identifying these points is the first step in deciding whether they require correction or removal. Now, let's put these concepts into practice by quantifying influence in our car dataset. First, we look at global influence using Cook's distance. By running predict d-Cookst and applying the common 4/n threshold, which is 4/74 for this data, we identify two major culprits, the Cadillac Seville and the VW Diesel. These cars have a substantial overall impact on the entire set of regression coefficients. Moving to the right, we examine parameter-specific influence using DFBETAS. This allows us to see how a single observation affects one specific variable. Look at the bar chart for the weight coefficient. With the VW Diesel included, the coefficient is 3.4. However, if we drop just this one car, the coefficient for weight jumps to 4.1. This massive shift proves that the VW Diesel was disproportionately dragging down the estimated effective weight, showing why checking for specific influence is so critical.
To wrap up, let's look at the final remediation strategy for our automobile model. We found 3 key issues. First, misspecification, which we fixed by adding a nonlinear term, like weight squared, to account for the nonlinear cost of car size. Second, collinearity between weight and length, which is solved by dropping the redundant length variable. Third, global influence confirmed by Cook's D, where the remedy is to keep the valid data but use robust regression, or RREG in Stata. Moving to the economist's decision matrix, we have a generalized framework for handling any anomaly. If it is a data error, we correct or delete it. If it is a valid outlier, we keep it, check sensitivity, and consider a log transform. If it is a model failure, we must respecify the functional form. I want to leave you with this thought. Diagnostics don't tell you which data to delete. They tell you which questions to ask. Use these statistics to investigate your data deeply, not just to sanitize it.